Hello and welcome to our journey through the lost pages of human history. Tonight, we are not just talking about another archaeological discovery or historical timeline, but about entire civilizations that have vanished beneath the waves of time itself. Something extraordinary lies hidden directly beneath our feet and beneath the oceans, true remnants of forgotten worlds existing after millennia of being lost to rising seas and shifting landscapes. These vanished lands, once called Doggerland, and countless other lost territories, are not merely underwater ruins. Unlike the civilizations we read about in history books, these forgotten worlds are messengers from humanity's deeper past, their secrets shrouded in mysteries more ancient than recorded history. What makes these lost civilizations even more astonishing isn't just their disappearance beneath unimaginable depths of ocean water, but the revelation that entire human societies once thrived, where today we see only empty seas, a reality that challenges everything we thought we knew about our ancestors. Before we plunge deeper into this archaeological enigma, imagine where you are right now in a familiar world, perhaps unaware that beneath the waves and buried landscapes, remnants of lost human stories could be rewriting everything we know about our past. If stories like this compel your imagination, consider subscribing or liking this program. It helps more curious minds connect and prepares us all to face the astonishing and sometimes unsettling truths that archaeology brings to light. Now take a moment. Let your mind reach back through time and prepare to grasp what it truly means for an entire civilization to vanish, for landscapes like Doggerland to disappear beneath rising seas, taking with them the untold stories of our ancestors. This is the beginning of a story where time itself becomes the ultimate eraser, and we must confront what we've lost as we piece together humanity's forgotten chapters beneath the waves. Imagine standing on a coastline that no longer exists. Picture walking along beaches that now lie beneath 400 feet of ocean water. These vanished landscapes once stretched for thousands of miles, connecting continents that today are separated by vast seas. 26,000 years ago, our planet looked fundamentally different. Earth's most recent ice age had reached its peak, with massive ice sheets covering vast portions of North America, Northern Europe, and Asia. These glaciers, some over a mile thick, locked away enormous quantities of water that today fill our oceans. Global sea levels stood at least 400 feet lower than they do now, exposing land masses that have since disappeared beneath the waves. The scale of this transformation challenges our understanding of ancient human geography, where today we see the North Sea between Britain and continental Europe. There once stretched a landscape researchers call Doggerland, a territory larger than modern-day Germany. This lost world contained rolling hills, river valleys, freshwater lakes, and vast plains that supported both human communities and diverse wildlife. Scientists have pieced together evidence of these vanished lands through decades of careful investigation. Fishing trawlers operating in the North Sea regularly drag up the bones of extinct mammals, mammoth tusks, rhinoceros skulls, and the remains of giant deer that once roamed the grasslands. Mixed among these ancient bones, archaeologists have discovered human artifacts, stone tools, antler harpoons, and evidence of sophisticated hunting communities that thrived in environments now lost to time. The transformation from Ice Age world to modern geography was neither gradual nor uniform. Research indicates that deglaciation began around 21,000 years ago, initiating what scientists describe as one of the most dramatic environmental changes in human history. Initially, sea levels rose slowly, but this period was punctuated by episodes of catastrophic change known as meltwater pulses. The most significant of these events occurred approximately 14,500 years ago. During a period lasting just 500 years, global sea levels rose by 60 feet at rates exceeding 40 millimeters per year, more than 10 times faster than current sea level rise. This pulse, designated Meltwater Pulse 1A by researchers, coincided with the onset of a major warming period in the northern hemisphere and likely resulted from the collapse of large sections of ice sheets. Archaeological evidence suggests human communities faced unprecedented challenges during these periods of rapid change. Settlements that had been established during the Ice Age maximum found themselves increasingly surrounded by rising waters. The inhabitants of Doggerland, for instance, witnessed their homeland transform from a vast continental plain into an archipelago of islands before finally disappearing entirely beneath the North Sea around 8,000 years ago. The final submersion of Doggerland may have been hastened by a catastrophic event. Recent analysis of sediment cores from the North Sea floor has revealed evidence of a massive tsunami that struck the region approximately 8,150 years ago. This tsunami, generated by an underwater landslide off the coast of Norway, may have delivered the final blow to the remaining inhabited islands of the once great land bridge. Similar stories of lost landscapes emerge from coastlines around the world. Off the northwestern coast of Australia, archaeologists have discovered stone tools and grinding implements on the seafloor at depths of up to 40 feet, marking the locations of Aboriginal camps that were once situated on dry land. These underwater archaeological sites represent the oldest known evidence of human occupation on what was once a much larger Australian continent. The Mediterranean Sea holds its own secrets of submerged civilizations. Rising waters have drowned not only natural landscapes, but also early human settlements. The prehistoric site of Atlit Yam, discovered 36 feet below the surface off the Israeli coast, preserves evidence of one of the world's earliest farming communities, complete with stone houses, ancient wells, and human burials dating back 9,000 years. Research teams have begun using advanced technology to map these lost worlds with unprecedented detail. Seismic surveys, originally conducted for oil exploration, have been repurposed to create three-dimensional reconstructions of submerged landscapes. These surveys reveal the locations of ancient rivers, lakes, and coastlines with remarkable precision, allowing archaeologists to predict where human settlements might have existed. The implications extend far beyond archaeological curiosity. These submerged landscapes may hold crucial evidence about the early development of agriculture, the origins of seafaring technology, and the first permanent coastal settlements. Many of the revolutionary changes that transformed human society including the transition from hunting and gathering to farming, occurred during this period of dramatic sea level change. Recent discoveries have revealed the sophisticated nature of these lost coastal societies. Analysis of artifacts recovered from submerged sites indicates that prehistoric communities possessed advanced knowledge of marine environments, developed complex fishing technologies, and established extensive trade networks that connected distant regions. The preservation conditions beneath the sea have maintained organic materials that would have long since decomposed on land, providing archaeologists with unprecedented insights into prehistoric life. The study of these submerged landscapes also offers important perspectives on human adaptability in the face of environmental change. Communities that survived the transition from Ice Age to modern climate demonstrated remarkable flexibility, developing new technologies for maritime environments and establishing settlements that could withstand dramatic environmental fluctuations. Continental shelves around the world contain similar archaeological treasures waiting to be discovered. The relatively shallow waters that now cover these former landmasses have preserved not only artifacts, but also the geological features that shaped prehistoric human settlement patterns. River channels, lake beds, and coastal dunes remain identifiable on the seafloor, creating a detailed record of ancient environments. Modern research techniques continue to reveal new details about these lost worlds. Advanced coring methods can extract sediment samples that preserve pollen grains, plant remains, and even ancient DNA, allowing scientists to reconstruct the vegetation and wildlife communities that supported prehistoric human populations. These biological indicators provide evidence of the rich ecosystems that flourished in areas now covered by hundreds of feet of ocean water. The transformation of these landscapes represents more than geographical change and marks a fundamental shift in human relationship with the environment. Communities that had developed sophisticated knowledge of inland resources and terrestrial hunting grounds were forced to adapt rapidly to coastal and maritime environments. This transition may have accelerated the development of seafaring technologies and deepened human understanding of marine ecosystems. Evidence from multiple continents suggests that sea level rise proceeded in stages, with periods of rapid change alternating with intervals of relative stability. These patterns provided prehistoric communities with opportunities to establish new settlements and develop adaptation strategies, but also subjected them to recurring episodes of displacement and environmental stress. The archaeological record from this period reveals evidence of both cultural continuity and innovation. While some traditional technologies and practices persisted, communities also developed new approaches to coastal living, marine resource exploitation, and long-distance transportation across water barriers. These innovations laid the foundation for later maritime civilizations and global exploration. As sea levels approached their current heights around 6,000 years ago, the geography we recognize today began to take shape. However, the memory of these lost lands may have persisted in oral traditions and cultural knowledge systems. Flood stories found in many ancient traditions may preserve collective memories of the dramatic coastal changes that shaped early human history. The study of these submerged archaeological sites continues to evolve as new technologies become available. Underwater excavation techniques, remote sensing methods, and advances in biological analysis are revealing ever more detailed pictures of these lost civilizations. Each discovery adds to our understanding of human adaptability and the complex relationship between environmental change and cultural development. These vanished landscapes remind us that the world our earliest ancestors inhabited was profoundly different from our own. The coastlines that seem permanent to us today are relatively recent features, established only after dramatic transformations that reshaped both the natural environment and human society. Before the waters rose to their current levels, entire civilizations flourished on lands that now lie hidden beneath the waves, their stories slowly emerging as archaeology reveals the secrets of our submerged past. Human hands shaped limestone into monuments that defied explanation. 11,000 years ago, when agriculture had not yet emerged and permanent settlements remained unknown, builders on a hilltop in southeastern Turkey carved pillars from solid bedrock with a precision that continues to puzzle modern engineers. The site they created, now called Göbekli Tepe, represents one of archaeology's most profound mysteries. These ancient architects extracted massive T-shaped columns directly from the limestone plateau, some weighing 50 tons and standing 23 feet tall. They carved intricate reliefs of animals, abstract symbols, and human hands into surfaces so smooth they appear almost polished. Yet these accomplishments preceded the supposed dawn of civilization by thousands of years. The engineering challenges faced by these prehistoric builders seem almost insurmountable when considered within the technological constraints of their time. Each pillar required quarrying techniques that could separate enormous blocks from solid bedrock without fracturing the stone or compromising the intended final form. Archaeological investigation has revealed the quarry sites where these monuments originated, marked by channels cut into the rock and unfinished columns still attached to the bedrock. Evidence from the quarries provides crucial insights into ancient stoneworking methods. Researchers have identified 3 partially completed T-shaped pillars that were never removed from their limestone matrix. The largest of these unfinished monuments measures 23 feet in length with a head width of nearly 10 feet, suggesting the builders possessed both the ambition and technical knowledge to work at tremendous scales. The quarrying process itself represented a remarkable feat of prehistoric engineering. Workers used stone tools to cut precise channels around the intended pillar, gradually separating it from the surrounding bedrock. This technique, known as profile pecking, involved repeatedly striking the limestone with harder stone implements to chip away material along predetermined lines. Experimental archaeology has demonstrated that skilled stone workers using basalt hammers could achieve the precision evident in the Göbekli Tepe quarries. Investigations at prehistoric quarries across Europe and the Mediterranean have revealed sophisticated understanding of stone properties and extraction techniques. At megalithic sites in the Balearic Islands, builders developed methods that exploited the natural characteristics of limestone formations. They identified weaknesses in the rock structure and used controlled applications of heat to separate large blocks with minimal waste of material. The fire-based quarrying method discovered at these sites involved cutting shallow trenches around standing limestone blocks, then building fires in these channels to create thermal shock that split the stone along desired lines. This technique required precise understanding of how different limestone types responded to heating and cooling cycles. Archaeological evidence shows that prehistoric quarry workers could predict exactly where stones would fracture, allowing them to extract blocks of predetermined dimensions. Transportation of quarried materials presented equally complex challenges. Moving 50-ton limestone columns across uneven terrain without modern machinery demanded innovative solutions and coordinated labor. Experimental studies suggest that teams of 20 to 75 people could transport such massive stones using combinations of ropes, wooden rollers, and carefully planned routes. The actual methods employed likely varied based on terrain and distance. Archaeological evidence from various megalithic sites indicates that builders used wooden sledges mounted on rolling logs for overland transport. This technique distributed weight across multiple contact points and reduced friction between the load and ground surface. Careful coordination of dozens of workers was essential to maintain momentum and prevent the massive stones from shifting during movement. Recent experiments have challenged earlier estimates of the labor requirements for megalithic construction. While some researchers initially calculated that moving a single large pillar required hundreds of workers, more refined studies suggest that skilled teams of 7 to 14 people could accomplish such tasks using efficient techniques with ropes and lubricants. These revised estimates indicate that megalithic construction may have been within the capabilities of extended family groups or small village communities, rather than requiring massive, centrally organized workforces. Precision positioning of these enormous stones represented another technical challenge that ancient builders solved with remarkable success. The pillars at Göbekli Tepe were not simply stood upright, but were arranged in complex circular patterns with specific spatial relationships. Achieving such precise alignments required sophisticated measurement techniques and careful planning of the entire construction sequence. Archaeological analysis has revealed that the builders employed geometric principles in laying out their circular enclosures. Recent studies suggest that 3 major enclosures at Göbekli Tepe were planned as components of a single hierarchical complex, forming an equilateral triangle. This level of geometric planning implies mathematical knowledge and surveying capabilities that extend far beyond simple monument construction. The carving techniques used to decorate these pillars demonstrate equally advanced skills. Using only stone tools, prehistoric artisans created detailed reliefs of animals, human figures, and abstract symbols. The precision of these carvings, particularly the fine details achieved in hard limestone, indicates mastery of percussion techniques and deep understanding of stone properties. Evidence from tool marks and carving patterns suggests that the artisans employed systematic approaches to relief creation. They first roughed out basic forms using harder stone hammers, then progressively refined details using smaller tools and careful percussion techniques. The consistency of carving styles across multiple pillars indicates either individual artisans working on multiple monuments or shared training traditions that maintain technical standards. Investigation of stoneworking tools from the site has provided additional insights into prehistoric craftsmanship capabilities. While metal tools were not available to Neolithic builders, they created sophisticated implements from available materials. Flint knapping produced razor-sharp blades suitable for fine detail work, while harder stones like basalt served as hammers for rough shaping. The tool assemblages recovered from megalithic sites reveal evidence of specialized craft production. Different tool types served specific functions in the stoneworking process, from initial quarrying through final surface finishing. This specialization implies organized approaches to monument construction, with different workers focusing on particular aspects of the building process. Analysis of construction sequences at various megalithic sites has revealed sophisticated project management capabilities. Builders coordinated multiple simultaneous activities, including quarrying, transport, site preparation, and monument erection. Archaeological evidence suggests that work proceeded according to predetermined plans, rather than improvised solutions developed during construction. The engineering solutions employed at sites like Göbekli Tepe required not only technical skill, but also profound understanding of structural mechanics. Supporting 50-ton vertical pillars demanded careful attention to foundation preparation and load distribution. The builders created stable foundations by carving pedestals directly into bedrock, ensuring that massive pillars would remain upright for millennia. Underground construction techniques at megalithic sites demonstrate additional engineering capabilities. Builders created complex interior spaces within earthen mounds and rock formations, requiring careful attention to structural stability and drainage. These hidden chambers often incorporated sophisticated architectural features, including corbelled ceilings and precisely fitted stone joints. The global distribution of megalithic construction techniques suggests either widespread development of similar technologies or transmission of knowledge across vast distances. Sites separated by thousands of miles and centuries of time demonstrate remarkably similar approaches to quarrying, transport, and construction challenges. This consistency implies either universal human solutions to engineering problems or early networks for sharing technical knowledge. Comparison of megalithic sites across different geological conditions reveals adaptive approaches to local material properties. Builders working with different stone types developed specialized techniques suited to their available materials. Limestone quarries employed different methods than those used for granite or sandstone extraction, demonstrating flexible application of fundamental engineering principles. Recent discoveries continue to expand understanding of prehistoric engineering capabilities. New archaeological sites regularly reveal evidence of construction techniques that challenge assumptions about ancient technological limitations. Each discovery adds to the growing recognition that prehistoric builders possessed sophisticated knowledge of materials science, structural engineering, and project management. Modern attempts to replicate ancient construction methods have provided valuable insights into the practical challenges faced by prehistoric builders. These experiments demonstrate both the feasibility of proposed techniques and the high levels of skill required for successful implementation. Contemporary stone workers using only traditional tools have gained new appreciation for the expertise of their ancient predecessors. The legacy of these prehistoric architects extends far beyond their immediate accomplishments. The techniques they developed for working stone, organizing labor, and managing complex construction projects established foundations for later architectural traditions. Their innovations in quarrying, transport, and precision placement influenced construction methods that persisted for thousands of years. These ancient stoneworkers left behind not only impressive monuments, but also evidence of human ingenuity and determination. Their achievements demonstrate that sophisticated engineering solutions can emerge from careful observation, systematic experimentation, and accumulated practical knowledge. The architects of stone created lasting testimonies to human capability that continue to inspire wonder and respect 11,000 years after their completion. Bronze emerged from furnaces with properties that seemed almost magical. 7,000 years ago, craftsmen discovered that mixing copper with small amounts of tin created an alloy superior to either metal alone. This achievement required knowledge of ore sources scattered across vast distances, mastery of high-temperature techniques, and understanding of chemical transformations that would not be scientifically explained for millennia. The earliest evidence of intentional bronze production dates to approximately 5,000 years ago in the ancient Near East, yet the sophisticated metallurgy revealed by archaeological analysis suggests a long period of experimentation and development that must have preceded these first documented successes. The complexity of bronze production implies accumulated knowledge spanning generations of metalworkers who refined their techniques through careful observation and systematic innovation. Creating bronze represented far more than simply melting two metals together. The process demanded precise control over temperature, timing, and composition. Copper melts at 1085 degrees Celsius, while tin liquefies at just 230 degrees Celsius. Despite this disparity, the optimal bronze alloy typically contained approximately 10% tin mixed with 90% copper. Achieving this ratio consistently required sophisticated understanding of how different proportions affected the final product's properties. Archaeological investigation has revealed that prehistoric metalworkers possessed detailed knowledge of how various additives influenced bronze characteristics. Analyses of Bronze Age artifacts show intentional variations in alloy composition depending on the intended use of each object. Weapons and cutting tools typically contained higher concentrations of tin, creating harder alloys capable of holding sharp edges. Decorative objects and vessels often incorporated small amounts of lead, which improved the metal's flow characteristics during casting while creating more intricate surface details. The inclusion of arsenic in early copper alloys represents another dimension of prehistoric metallurgical sophistication. Arsenical copper, containing up to 8% arsenic, appeared in archaeological contexts before true tin bronze became widespread. This alloy offered significant advantages over pure copper, including increased hardness and improved workability during forging operations. The presence of arsenic also acted as an antioxidant during casting, reducing gas porosity and creating stronger final products. Evidence suggests that the addition of arsenic to copper was intentional rather than accidental. While arsenic occurs naturally in some copper ores, the consistent proportions found in archaeological specimens indicate deliberate control over alloy composition. Prehistoric metalworkers must have recognized that certain ore sources produced superior results and developed methods to achieve consistent arsenic content in their finished products. The technical challenges of bronze production extended far beyond alloy composition. Smelting copper ore required furnaces capable of reaching temperatures exceeding 1,000 degrees Celsius. Archaeological excavations at prehistoric mining sites have revealed sophisticated furnace designs that maximized heat efficiency while minimizing fuel consumption. These installations typically featured pit furnaces lined with clay and equipped with bellows systems to force air through the burning charcoal. The Great Orme copper mine in Wales provides exceptional evidence for Bronze Age metallurgical practices. Active during the Middle Bronze Age, between 3,900 and 2,900 years ago, this site produced an estimated total of over 7 tons of copper annually. The scale of production suggests organized industrial activity requiring coordination of mining, ore processing, fuel production, and smelting operations. Experimental reproduction of ancient smelting techniques has demonstrated the sophistication required for successful copper extraction. Modern attempts to replicate Bronze Age methods using primitive furnaces show that achieving complete ore reduction demanded careful attention to airflow, temperature control, and chemical composition of the ore mixture. Even small variations in these parameters could result in incomplete smelting and substantial loss of valuable copper. The lost wax casting technique represents another remarkable achievement of prehistoric metalworkers. This process, used to create complex bronze objects with intricate details, required exceptional skill and understanding of thermal properties. Archaeological evidence indicates that lost wax casting was practiced at least 6,500 years ago, with the oldest known examples discovered at Bulgaria's Varna necropolis. The lost wax process involved creating a detailed wax model of the desired object, covering it with clay to form a mold, then heating the assembly to melt out the wax while hardening the clay. Molten bronze was then poured into the cavity left by the melted wax. This technique allowed prehistoric craftsmen to produce objects with wall thicknesses and surface details impossible to achieve through hammering or simple casting methods. Analysis of Bronze Age lost wax castings reveals remarkable precision in both execution and planning. The process required accurate calculation of wax volumes, metal quantities, and pouring temperatures. Mistakes in any of these parameters could result in incomplete casting or structural failure. The consistency of results achieved by prehistoric metalworkers indicates systematic approaches to quality control and standardized procedures. The complexity of bronze production extended to the procurement of raw materials. Tin deposits suitable for bronze making are geographically rare, found primarily in regions such as Cornwall, Bohemia, and parts of Central Asia. Evidence from Bronze Age sites across Europe shows that tin was transported over distances exceeding 1,000 miles, indicating extensive trade networks dedicated to metalworking supplies. The establishment of these long-distance trade routes for tin represents a significant organizational achievement. Prehistoric societies had to develop systems for identifying, extracting, and transporting relatively small quantities of tin ore across difficult terrain. The high value of tin relative to its weight made such transportation economically viable, but required sophisticated knowledge of ore sources and reliable trading relationships. Archaeological evidence suggests that Bronze Age metalworkers also understood the principles of metal recycling. Hoards of broken bronze objects have been discovered throughout Europe, containing fragments of swords, axes, and tools cut to sizes suitable for remelting. These recycling practices indicate that bronze was treated as a valuable resource to be conserved and reused rather than discarded when objects became damaged or obsolete. The metallurgical knowledge required for successful bronze production was preserved and transmitted through generations of specialized craftsmen. Analysis of tool marks and manufacturing techniques shows remarkable consistency in methods used across wide geographical areas and extended time periods. This consistency suggests the existence of training traditions that maintained technical standards and passed complex knowledge from master metalworkers to apprentices. Recent discoveries continue to expand understanding of prehistoric metallurgical capabilities. Archaeological excavations in China at the Tonglushan site have revealed evidence of sophisticated copper smelting techniques dating back over 3,000 years. These operations incorporated multiple stage processing methods that maximized copper recovery from complex sulfide ores while minimizing environmental impacts. The slag deposits left by prehistoric smelting operations provide crucial insights into ancient techniques. Chemical analysis of these waste products reveals information about ore types, furnace temperatures, and processing methods employed by ancient metalworkers. The composition and structure of slags indicate that prehistoric furnaces achieved thermal conditions previously thought impossible without modern technology. Multi-stage smelting processes were employed at some Bronze Age sites to extract copper from sulfide ores. These complex operations involved initial roasting to remove sulfur, followed by reduction smelting to produce metallic copper. Archaeological evidence suggests that prehistoric metalworkers understood the chemical relationships involved and developed systematic approaches to optimize copper recovery from challenging ore types. The social implications of bronze production extended far beyond technical achievements. The concentration of metallurgical knowledge in specialized craftsmen created new forms of social organization and economic relationships. Bronze objects became symbols of status and wealth, with elaborate weapons and ornaments serving to demonstrate the power and resources of their owners. Control over bronze production may have contributed to the emergence of centralized political authority in Bronze Age societies. The resources required for large-scale metallurgy, including access to ore deposits, fuel supplies, and skilled craftsmen, could be most effectively organized by powerful leaders capable of coordinating complex production systems. Archaeological evidence from Bronze Age settlements shows increasing social stratification corresponding with the development of metallurgical industries. The technological achievements of prehistoric metalworkers established foundations for subsequent developments in materials science and engineering. The techniques they developed for controlling alloy composition, managing high-temperature processes, and creating complex cast objects influenced metalworking practices that persisted for thousands of years. Their innovations in furnace design, heat treatment, and quality control contributed to technological traditions that ultimately led to iron production and industrial metallurgy. Modern analysis of Bronze Age metallurgy reveals the sophisticated nature of prehistoric technical knowledge. Using only empirical observation and experimental learning, ancient craftsmen developed understanding of chemical principles that would not be formally explained until the development of modern chemistry. Their achievements demonstrate human capability for systematic investigation and technical innovation, operating within the constraints of available technology and materials. The legacy of Bronze Age metalworkers extends beyond their technical innovations to include their contributions to human civilization. The development of bronze technology facilitated agricultural improvements, military advances, and artistic achievements that shaped the course of human history. Their mastery of metallurgical processes represented a crucial step in humanity's relationship with materials science and technological development. The secrets of these ancient metalworkers were hard-won through generations of experimentation, observation, and accumulated experience. Their achievements in creating sophisticated alloys, mastering high-temperature processes, and developing complex manufacturing techniques established technological foundations that supported the development of civilization itself. The knowledge they preserved and transmitted through their craft traditions represents one of humanity's earliest examples of systematic technical innovation. What secrets lie beneath the Mediterranean waves? Between 3 and 4 meters below the surface of Vatica Bay in Greece, archaeologists have mapped the remains of an entire Bronze Age city. Streets, buildings, courtyards, and tombs stretch across an area equivalent to 7 football pitches, preserved in remarkable detail by their submersion 5,000 years ago. This underwater settlement, known today as Pavlopetri, represents something unprecedented in archaeology, a nearly complete urban plan from the Bronze Age. Unlike other ancient sites where only foundations or fragments survive, Pavlopetri offers a comprehensive view of how prehistoric cities were organized, how people lived within them, and what sophisticated planning principles guided their construction. The discovery of Pavlopetri began in 1967 when British oceanographer Nicholas Fleming noticed unusual geometric patterns in aerial photographs of the seafloor. These regular lines and shapes, visible through the clear Mediterranean waters, proved to be the remains of streets, building foundations, and other urban infrastructure. Systematic mapping revealed a settlement of extraordinary complexity for its time period. Archaeological investigation has shown that Pavlopetri was carefully planned according to sophisticated urban design principles. The city features well-constructed roads connecting different districts, with residential areas organized around central courtyards. Larger buildings, possibly serving public or religious functions, occupy strategic locations within the urban layout. The presence of chamber tombs carved into stone indicates established burial practices and likely social hierarchies within the community. The level of urban planning evidenced at Pavlopetri challenges assumptions about Bronze Age settlement organization. The city displays systematic street layouts with residential neighborhoods arranged in orderly patterns. Archaeological evidence suggests the presence of a water management system with channels and pipes running alongside streets. This infrastructure implies coordinated community efforts to provide essential services to urban residents. Detailed mapping has revealed that Pavlopetri contained distinct functional areas serving different purposes. The harbor district included warehouses and facilities for loading and unloading trading vessels. Residential quarters featured both single-story and two-story houses, with evidence suggesting that more affluent families occupied larger multi-level structures. Industrial areas contained workshops for pottery production and textile manufacturing, indicating specialized craft production within the urban environment. The preservation conditions at Pavlopetri have maintained architectural details that would have been lost at terrestrial sites. Underwater excavation has revealed building foundations, wall remnants, and even interior features such as hearths and storage areas. The anaerobic environment beneath the seafloor has prevented the decay of organic materials, providing insights into construction techniques and daily life activities that are rarely preserved elsewhere. Similar underwater archaeological sites around the Mediterranean reveal patterns of sophisticated urban planning in prehistoric periods. Off the coast of Israel, the Neolithic settlement of Tel Huris demonstrates advanced understanding of coastal engineering. Dating to 7,000 years ago, this site includes a massive stone seawall over 100 meters long, constructed to protect the settlement from rising sea levels and storm surge. The Telluride seawall represents the earliest known example of coastal defense engineering, built from large rounded boulders transported from riverbeds over 3 kilometers away. This structure required coordinated community effort and sophisticated understanding of marine processes. Archaeological analysis indicates that the wall was specifically positioned to protect the inhabited areas from wave action and swash zone encroachment during storms. The construction techniques employed at Tel Hurs demonstrate remarkable engineering knowledge for the Neolithic period. The builders selected boulders weighing hundreds of kilograms and arranged them in a linear pattern designed to absorb wave energy. The wall's position and orientation show understanding of coastal dynamics, including seasonal variations in sea level and storm patterns. This level of environmental knowledge implies generations of careful observation and accumulated experience. Archaeological evidence from submerged settlements across the Mediterranean suggests that prehistoric communities possess sophisticated understanding of hydraulic engineering. Sites in the Black Sea region have revealed complex harbor systems with artificial breakwaters and docking facilities. These installations require detailed knowledge of tidal patterns, sediment transport, and structural engineering principles. The scale of these underwater archaeological sites indicates that prehistoric urban settlements were larger and more complex than previously recognized. Recent estimates suggest that over 3 million shipwreck sites and submerged settlements exist worldwide, representing an immense repository of archaeological information about past civilizations. The preservation conditions in marine environments have maintained evidence of urban planning, engineering capabilities, and social organization that would have been lost at terrestrial sites. Advanced technology has revolutionized the study of underwater archaeological sites. Three-dimensional mapping techniques using sonar and photogrammetry have enabled archaeologists to create detailed reconstructions of submerged settlements. These methods reveal architectural features, street layouts, and infrastructure systems with unprecedented precision, allowing researchers to understand prehistoric urban development in ways that were previously impossible. The use of autonomous underwater vehicles and remote sensing equipment has expanded the scope of underwater archaeological investigation. These technologies can survey large areas of seafloor systematically, identifying new sites and documenting existing ones in detail. Digital documentation creates permanent records of archaeological features that may be threatened by coastal development, pollution, or climate change. Recent discoveries continue to expand understanding of prehistoric underwater settlements. Marine archaeologists working in different regions have identified submerged sites dating from various time periods, each contributing to knowledge about ancient urban planning and engineering capabilities. The consistency of sophisticated design principles across widely separated sites suggests either common cultural traditions or fundamental human approaches to urban development. The study of submerged archaeological sites provides unique insights into prehistoric responses to environmental change. Many underwater settlements appear to have been abandoned due to rising sea levels, earthquakes, or other environmental pressures. Archaeological evidence from these sites reveals how ancient communities adapted their infrastructure and settlement patterns to cope with changing conditions. Water management systems discovered at underwater archaeological sites demonstrate sophisticated understanding of hydraulic principles. Petri and other submerged settlements include evidence of drainage systems, water storage facilities, and channel networks designed to control water flow through urban areas. These installations suggest that prehistoric communities could plan and construct complex infrastructure projects requiring coordinated labor and technical expertise. The preservation of organic materials at underwater sites has provided exceptional insights into prehistoric construction techniques and daily life activities. Wooden structural elements, textile fragments, and other perishable materials rarely survive at terrestrial archaeological sites, but can be preserved in anaerobic underwater environments. This evidence reveals aspects of prehistoric technology and craftsmanship that would otherwise be unknown. Archaeological investigation of submerged settlements has revealed evidence of extensive trade networks connecting prehistoric communities across the Mediterranean. Pottery fragments from Crete found at Petri indicate long-distance commercial relationships, while the presence of specialized workshops suggests local production for trade purposes. These economic connections required sophisticated maritime technology and navigation capabilities. The social implications of prehistoric urban planning revealed at underwater sites extend beyond technical achievements. The organization of space within these settlements reflects social hierarchies, community decision-making processes, and cultural values. The presence of public buildings, residential districts of varying quality, and specialized activity areas suggests complex social structures operating within these ancient communities. Contemporary threats to underwater archaeological sites highlight the urgency of documentation and preservation efforts. Rising sea levels, ocean acidification, and coastal development pose significant risks to submerged cultural heritage. Marine archaeologists are racing to document threatened sites before they are damaged or destroyed by environmental changes and human activities. The application of advanced preservation techniques is becoming essential for protecting underwater archaeological sites. Methods include physical protection using sand covers or barriers, legal protection through designation as marine protected areas, and digital preservation through detailed three-dimensional documentation. These approaches aim to safeguard archaeological resources for future research while allowing continued study of their significance. International cooperation has become crucial for the study and protection of underwater cultural heritage. The UNESCO Convention on the Protection of Underwater Cultural Heritage provides framework for coordinating research efforts and establishing protection standards. Collaborative projects involving multiple countries have enabled comprehensive investigation of sites that cross political boundaries. The scientific value of underwater archaeological sites extends beyond their historical significance to include their potential for understanding environmental change and human adaptation. These sites preserve evidence of past climate conditions, sea level variations, and ecosystem changes that can inform current understanding of environmental processes. Archaeological data from submerged settlements contributes to climate research and coastal management planning. Modern underwater archaeological techniques continue to evolve, incorporating new technologies and methods. Advances in diving equipment, remote sensing capabilities, and data processing allow researchers to investigate sites that were previously inaccessible. These developments are expanding the scope of underwater archaeology and revealing new aspects of prehistoric civilization. The patterns revealed by underwater archaeological investigations demonstrate that sophisticated urban planning and engineering capabilities existed in prehistoric times. These achievements required accumulated knowledge, coordinated community effort, and systematic approaches to problem solving that challenge conventional assumptions about ancient technological limitations. The evidence preserved beneath the waves continues to reshape understanding of human civilization's depth and complexity. On a clear night 5,000 years ago, people stood among great stone circles and observed celestial movements with precision that rivals modern measurements. These Neolithic astronomers tracked not only the obvious cycles of sun and moon, but also the subtle 18-year rhythm of lunar standstills and the slow precession of stars across centuries. The sophistication of prehistoric astronomical knowledge becomes evident when examining the alignments built into megalithic monuments across northwestern Europe. Stone circles from the British Isles to Brittany display careful orientation towards specific celestial events, suggesting systematic observation and mathematical understanding that developed over many generations. At Stonehenge, the most famous of these ancient observatories, archaeologists have identified multiple astronomical alignments spanning different construction phases. The monument's main axis points toward midsummer sunrise in one direction and midwinter sunset in the opposite direction. This primary alignment, evident from the earliest phases of construction, demonstrates that celestial observation was fundamental to the site's conception and purpose. More subtle alignments at Stonehenge reveal deeper astronomical knowledge. The station's stone rectangle, positioned around the main stone circle, appears to track the extreme positions of the moon during its 18 6/10 year cycle. During this period, the moon's rising and setting positions shift between maximum northern and southern limits, a phenomenon known as lunar standstills that requires decades of careful observation to detect and predict. The precision of these alignments suggests that Neolithic builders possessed sophisticated understanding of celestial mechanics. Modern analysis of stone circle orientations reveals consistent patterns across hundreds of sites, indicating shared knowledge systems rather than coincidental arrangements. This widespread consistency implies either cultural transmission of astronomical information or independent development of similar observational techniques by communities separated by significant distances. Archaeological investigation has revealed that different types of stone circles serve different astronomical functions. Recumbent stone circles, found primarily in Scotland, feature large horizontal stones positioned between two upright flankers. These distinctive monuments consistently orient toward southern skylines, suggesting they were designed to frame specific star rises or lunar events. The positioning of the recumbent stone creates a natural sightline that would have enabled precise observations of celestial bodies near the horizon. Axial stone circles, particularly common in Ireland, employ tall portal stones positioned at circle entrances. These imposing megaliths frequently align with lunar extreme positions, indicating their builders understood the complex geometry of lunar motion. The portal stones function as monumental sighting devices, directing observers' attention towards specific areas of the sky where significant celestial events occur. The mathematical precision required for these alignments demonstrates advanced planning capabilities. Recent analysis of megalithic alignments using modern surveying techniques has confirmed that stone rows and circles were laid out with accuracy approaching 1 degree. This level of precision requires not only careful observation, but also systematic methods for transferring angular measurements from sky to ground. Evidence suggests that prehistoric astronomers developed techniques for predicting celestial events years in advance. The 19-year Metonic cycle, which aligns lunar phases with solar seasons, was known to Greek astronomers, but appears to have been understood much earlier by megalithic builders. Stone circle alignments that incorporate this cycle indicate long-term observation programs spanning multiple generations. The discovery of precession by ancient astronomers represents one of the most sophisticated achievements in prehistoric science. Precession, the slow wobble of Earth's axis that causes star positions to shift gradually over centuries, completes a full cycle approximately every 26,000 years. Detecting this subtle motion requires comparing stellar observations separated by several human lifetimes, suggesting institutional continuity in astronomical programs. Greek astronomer Hipparchus is usually credited with discovering precession around 150 years before the Common Era. However, recent analysis suggests that evidence for precessional awareness may exist in much older astronomical sites. Stone circles that align with star positions calculated for their construction dates, but not for later periods, might indicate that their builders understood how stellar alignments would change over time. The development of accurate calendars based on astronomical observation represents another achievement of prehistoric star watchers. Ancient civilizations worldwide created systems for tracking seasonal cycles, religious festivals, and agricultural activities using celestial markers. These calendars require detailed knowledge of solar and lunar cycles, as well as techniques for reconciling the incompatible lengths of lunar months and solar years. Egyptian astronomers developed one of the earliest solar calendars based on observations of Sirius, the brightest star in the sky, the heliacal rising of Sirius, when the star first becomes visible before dawn after a period of conjunction with the sun, coincided with the annual flooding of the Nile River. This correlation allowed Egyptian priests to predict the flood timing months in advance, providing crucial information for agricultural planning. Babylonian astronomers made equally impressive achievements in lunar observation. They developed sophisticated methods for predicting eclipses using the Saros cycle, an 18-year-plus period after which eclipses repeat in similar patterns. This discovery required systematic record-keeping over many eclipse cycles and mathematical techniques for analyzing cyclical patterns in complex astronomical data. The astronomical achievements of Mesoamerican civilizations demonstrate independent development of sophisticated observational techniques. Maya astronomers created complex calendar systems incorporating multiple overlapping cycles based on observations of Sun, Moon, and Venus. Their calculations were so accurate that Maya-Venus tables could predict the planet's positions centuries in advance with errors of only a few days. Maya astronomical knowledge included understanding of eclipse prediction, planetary cycles, and the precession of Venus visibility patterns. They developed mathematical techniques for handling large numbers and calculated astronomical cycles extending thousands of years into past and future. This level of computational sophistication rivals achievements of Old World astronomers and demonstrates universal human capacity for systematic celestial observation. The preservation of astronomical knowledge through oral traditions suggests sophisticated methods for transmitting technical information across generations. Many indigenous cultures worldwide maintained detailed knowledge of star positions, seasonal indicators, and calendar systems through memorized teachings passed from elders to students. These oral traditions often incorporated astronomical information into mythological narratives that aided memory and cultural transmission. Archaeological evidence indicates that astronomical observation sites were used continuously for centuries or millennia. Stonehenge underwent multiple phases of reconstruction and modification over 1,500 years, suggesting sustained institutional commitment to astronomical activities. The consistency of alignments across these different phases indicates preservation of original astronomical purposes, despite changes in construction techniques and architectural styles. Modern statistical analysis has confirmed the astronomical significance of megalithic alignments while eliminating chance explanations. Computer modeling of stone circle orientations, compared with random distributions, demonstrates that alignments with celestial events occur far more frequently than would be expected by coincidence. These statistical studies provide objective confirmation of intentional astronomical orientation in prehistoric monuments. The integration of astronomical knowledge with religious and social practices reveals the central role of celestial observation in prehistoric societies. Stone circles served not merely as observatories, but as ceremonial centers where communities gathered to mark seasonal transitions and celestial events. The combination of practical astronomical functions with ritual activities suggests that sky watching was embedded in broader cultural systems rather than pursued as abstract science. Recent discoveries continue to expand understanding of prehistoric astronomical capabilities. New analysis techniques, including computer modeling and satellite imagery, reveal alignments and patterns that were not evident to earlier researchers. These discoveries suggest that the sophistication of ancient astronomical knowledge may exceed even current estimates. The study of ancient astronomy provides insights into human cognitive development and cultural evolution. The ability to detect subtle celestial patterns, develop mathematical models for prediction, and transmit complex technical knowledge across generations represents significant achievements in human intellectual history. These accomplishments demonstrate that sophisticated analytical thinking and systematic investigation have characterized human cultures for thousands of years. The legacy of prehistoric astronomers extends beyond their technical achievements to include their contribution to fundamental human understanding of cosmic order. Their systematic observations and mathematical analyses established foundations for scientific thinking that influenced subsequent developments in astronomy, mathematics, and natural philosophy. The star watchers of the Neolithic period were not primitive observers, but sophisticated scientists whose work contributed to humanity's ongoing quest to understand its place in the universe. Buried in volcanic ash near Pompeii, archaeologists discovered a collection of surgical instruments so sophisticated they could perform operations that challenged medical practitioners well into the modern era. Bronze forceps, scalpels, and bone drills lay preserved alongside complex mechanical devices that demonstrate manufacturing precision rarely associated with ancient civilizations. The Antikythera mechanism stands as perhaps the most extraordinary example of ancient technological sophistication, recovered from a Roman-era shipwreck off the Greek island of Antikythera. This bronze device contains over 30 intricate gear wheels arranged in multiple layers. Modern analysis has revealed that this mechanism could calculate the positions of sun, moon, and planets, predict eclipses, and track the 4-year cycle of Olympic Games with remarkable accuracy. The precision required to manufacture the Antikythera mechanism challenges assumptions about ancient technological capabilities. The device's gear ratios correspond exactly to astronomical periods known from ancient texts, indicating that its creators possessed both detailed observational data and sophisticated mathematical understanding. The smallest gear wheels contain teeth barely 2 millimeters wide, requiring manufacturing techniques and measuring instruments of exceptional accuracy. Recent three-dimensional scanning has revealed additional complexities within the mechanism that were invisible to earlier researchers. The device incorporates differential gears, a technology not rediscovered until medieval Islamic clockmakers developed similar systems over 1,000 years later. This advanced mechanical engineering suggests the existence of a sophisticated tradition of precision instrument making in the ancient Mediterranean. Archaeological evidence from multiple sites indicates that the Antikythera mechanism was not unique, but represented one example of a broader technological tradition. References in ancient texts describe similar devices used for astronomical calculation, while archaeological discoveries have revealed fragments of comparable mechanisms from other locations. These findings suggest that complex mechanical instruments were more widespread in the ancient world than previously recognized. The manufacturing techniques required for ancient precision instruments demanded specialized knowledge and tools. Bronze casting for intricate mechanical components required furnaces capable of maintaining precise temperatures while controlling the cooling rate to prevent distortion. The consistent dimensions of gear teeth and axles indicate the use of measuring instruments accurate to fractions of millimeters, implying sophisticated metrology systems. Harappan civilization sites have yielded evidence of standardized measurement systems with precision approaching modern industrial standards. Weights and measures discovered at Mohenjo-Daro and other Indus Valley cities show remarkable consistency across the entire civilization, suggesting centralized standards and quality control systems. The accuracy of these measurement devices indicates advanced understanding of mathematical relationships and sophisticated manufacturing techniques. Analysis of Harappan precision instruments reveals manufacturing capabilities that rival modern production methods. Bronze and stone weights vary by less than 1% from their intended values across sites separated by hundreds of kilometers. This consistency required not only accurate master standards, but also techniques for reproducing precise measurements and systematic approaches to quality control throughout the manufacturing process. Evidence from ancient Egypt demonstrates sophisticated understanding of optical principles in lens manufacturing. Crystal and glass lenses discovered in Egyptian tombs show careful attention to surface quality and precise curvature. These optical devices required understanding of light refraction and grinding techniques capable of producing smooth, accurately shaped surfaces from hard materials. The Nimrud lenses, discovered at the ancient Assyrian capital, represent another example of advanced optical technology. These rock crystal lenses, dating to approximately 700 years before the Common Era, show evidence of sophisticated grinding and polishing techniques. The optical quality of these lenses suggests they may have been used for magnification or possibly even primitive telescopic observation. Medical instruments recovered from ancient sites demonstrate remarkable sophistication in both design and manufacturing. Roman surgical tools include complex multi-component devices with moving parts, springs, and precisely fitted joints. The manufacturing precision required for these instruments indicates advanced metalworking techniques and understanding of mechanical principles that would not be exceeded until relatively recent times. Archaeological investigation has revealed evidence of systematic approaches to tool standardization in ancient workshops. Bronze Age foundries show evidence of standard patterns or templates used to ensure consistency in tool production. This standardization implies organized manufacturing systems with quality control procedures and specialized craftsmen trained in specific production techniques. The development of precision measuring instruments represents a crucial achievement in ancient technology. Archaeological evidence indicates that ancient craftsmen developed techniques for creating accurate rulers, angle measures, and leveling devices. These instruments were essential for construction projects, manufacturing consistency, and scientific observation, suggesting widespread understanding of measurement principles. Recent analysis of ancient Chinese bronze working has revealed extraordinary precision in alloy composition and casting techniques. Bronze vessels from the Shang and Zhou dynasties show consistent alloy ratios and wall thicknesses that indicate sophisticated temperature control and quality management systems. The precision of these products suggests advanced understanding of metallurgical science and systematic approaches to craft production. The lost wax casting techniques used for complex ancient bronzes required exceptional skill and understanding of thermal properties. Multi-component bronze vessels with intricate decorative elements and precise fitting parts demonstrate mastery of complex manufacturing processes. The consistency of results achieved by ancient founders indicates systematic approaches to technique development and knowledge transmission between craftsmen. Water-powered machinery from ancient sites indicates sophisticated understanding of mechanical engineering principles. Archaeological evidence from Roman and Chinese sites reveals the use of water wheels, gear systems, and automated mechanisms for various industrial processes. These installations required understanding of power transmission, mechanical advantage, and precision engineering that rivals later medieval technology. The preservation of organic materials at some archaeological sites has provided insights into ancient woodworking and textile production technologies. Wooden mechanisms, loom components, and precision carpentry joints demonstrate advanced understanding of material properties and manufacturing techniques. The sophistication of these products suggests highly developed craft traditions with systematic approaches to skill development. Ancient glassmaking technology demonstrates remarkable understanding of chemistry and thermal control. Archaeological evidence from Roman and Islamic sites reveals techniques for producing clear glass, colored glass, and optical components with consistent properties. The precision of ancient glass products indicates sophisticated understanding of furnace design, temperature management, and chemical formulation. The development of precision timekeeping devices in ancient civilizations required integration of astronomical observation mechanical engineering and manufacturing precision. Water clocks, sundials, and mechanical timepieces from various cultures show careful attention to accuracy and consistency. These devices represent convergence of multiple technical disciplines and demonstrate the sophisticated nature of ancient scientific instrument making. Modern reverse engineering of ancient mechanisms continues to reveal new aspects of their sophistication. Computer modeling and precision measurement techniques allow researchers to understand manufacturing methods and design principles that were not apparent to earlier investigators. These studies consistently demonstrate that ancient technological achievements exceeded previous estimates of their capabilities. The social and economic implications of ancient precision manufacturing extend beyond technical achievements. The development of sophisticated tools and instruments required specialized knowledge, organized production systems, and trade networks for raw materials. These technological capabilities contributed to social stratification, economic development, and cultural exchange that shaped the development of complex civilizations. International collaboration among ancient craftsmen is evidenced by the distribution of similar technologies across vast geographical areas. Precision instruments and manufacturing techniques appear in widely separated cultures with remarkable consistency, suggesting either technological diffusion through trade networks or independent development of similar solutions to common technical challenges. The tools and instruments created by ancient craftsmen established technological foundations that influenced subsequent developments for thousands of years. Their innovations in precision manufacturing, mechanical engineering, and materials science contributed to technological traditions that ultimately led to industrial development and modern manufacturing systems. The legacy of ancient toolmakers extends beyond their immediate technical achievements to include their contribution to human understanding of precision, measurement, and systematic manufacturing. Their development of sophisticated instruments and techniques demonstrates the long history of human technological innovation and the continuous quest for improved tools and methods that characterizes human civilization. Stories preserve what stones cannot tell. Across isolated cultures, separated by oceans and continents, remarkably similar narratives describe catastrophic floods, falling skies, and worlds destroyed by fire. These tales, dismissed by some as mere mythology, may actually represent humanity's oldest historical records, collective memories of real events encoded in oral traditions and passed down through countless generations. The global distribution of flood narratives presents one of the most compelling examples of shared cultural memory, from the Mesopotamian epic of Gilgamesh to Aboriginal Australian Dreamtime stories, from Hindu Puranas to Native American traditions. Cultures worldwide preserve detailed accounts of devastating floods that reshaped the earth. The consistency of these narratives across cultures with no historical contact suggests they may reflect common experiences of actual geological events. Recent archaeological and geological research has revealed that many flood stories contain surprisingly accurate environmental information. Aboriginal Australian oral traditions describe the flooding of coastal plains and the formation of islands that correlate precisely with sea level changes documented by marine geologists. These stories, maintained through oral transmission for thousands of years, preserve details of landscape transformation that occurred during post-glacial flooding. The preservation of astronomical events in cultural narratives demonstrates sophisticated methods for encoding and transmitting technical information through storytelling. Many cultures worldwide maintain stories describing changes in star patterns, the appearance of new celestial objects, and alterations in seasonal cycles. These narratives often contain specific details about stellar positions and celestial movements that correspond to real astronomical phenomena. Analysis of Nordic and Germanic mythological traditions has revealed possible descriptions of actual historical events with astronomical components. The Ragnarok narratives describe a series of catastrophic events, including changes in solar behavior, disruption of seasonal patterns, and the appearance of unusual celestial phenomena. Some researchers propose that these stories may preserve memories of extreme climate events or cosmic impacts that affected northern European populations. Greek mythological accounts contain detailed descriptions of geological phenomena that correlate with specific events documented in the archaeological record. The myth of Phaethon, traditionally interpreted as a moralistic tale, describes environmental changes consistent with the effects of a cosmic impact or massive volcanic eruption. The geographical specificity of these accounts suggests they may preserve memories of actual catastrophic events that affected ancient Mediterranean civilizations. Indigenous traditions from the Americas demonstrate sophisticated understanding of long-term environmental cycles and geological processes. Pueblo cultures maintain detailed oral histories describing changes in precipitation patterns, river courses, and vegetation communities spanning many centuries. These traditional knowledge systems provide insights into regional environmental history that complement and extend scientific paleoclimatic records. The integration of practical knowledge with narrative frameworks enabled ancient cultures to preserve complex information without written records. Astronomical observations, seasonal indicators, and navigational techniques were embedded in stories that served multiple functions as entertainment, education, and cultural transmission. This integration ensured the preservation of essential technical knowledge across generations through memorable and engaging narratives. Cultural transmission mechanisms developed by prehistoric societies enabled the maintenance of detailed technical information over vast time periods. Professional storytellers, ritual specialists, and trained memorists maintain strict accuracy in the preservation and transmission of traditional knowledge. These human libraries preserve not only stories, but also the technical and environmental information encoded within them. Archaeological evidence supports the historical basis for many traditional narratives previously dismissed as purely mythological. Excavations at sites described in oral traditions have revealed physical evidence confirming details preserved in stories. The ancient city of Troy, long considered purely legendary, was discovered through careful attention to geographical details preserved in Homer's epic poems. Geological and climatic events recorded in oral traditions provide valuable scientific information about past environmental conditions. Stories describing specific patterns of drought, flood, volcanic activity, and seismic events offer insights into regional geological history that extend far beyond the reach of written records. These oral archives preserve environmental data covering time periods much longer than conventional historical sources. The specificity of environmental details preserved in oral traditions indicates systematic observation and careful cultural transmission. Many stories include precise information about seasonal timing, geographical locations, and environmental conditions that could only be preserved through accurate observation and faithful transmission across generations. The consistency of these details suggests sophisticated methods for maintaining information integrity in oral cultures. Modern verification of traditional knowledge has confirmed the accuracy of information preserved through oral transmission. Scientific investigation of geographical features, environmental conditions, and historical events described in traditional stories has repeatedly validated the accuracy of orally transmitted information. These confirmations demonstrate the reliability of oral tradition as a historical source when properly interpreted and analyzed. The symbolic encoding of technical information in mythological narratives served multiple purposes in prehistoric cultures. Complex astronomical data, seasonal indicators, and geographical knowledge were embedded in memorable story formats that facilitated transmission while preserving accuracy. This encoding allowed technical information to be shared widely while maintaining the precision necessary for practical applications. Comparative analysis of global mythological traditions reveals common elements that suggest shared origins or common experiences. Similar narrative structures, character types, and event sequences appear in cultures separated by vast distances and time periods. These commonalities may reflect either cultural diffusion through ancient contact networks or independent responses to similar environmental challenges and cosmic events. The correlation between traditional stories and scientific evidence for past catastrophic events suggests that oral traditions may preserve the longest historical records available to humanity. Some narratives appear to describe environmental changes that occurred thousands of years before the development of writing systems. If accurate, these oral records extend human historical knowledge far beyond the reach of conventional archaeological and written sources. Recent disasters have provided opportunities to observe how catastrophic events become integrated into oral traditions. Modern documentation of how communities process and transmit memories of earthquakes, tsunamis, and volcanic eruptions offers insights into the mechanisms by which historical events become encoded in cultural narratives. These contemporary examples help researchers understand how ancient events may have been preserved in traditional stories. Climate science has found valuable information in traditional knowledge systems that extend scientific understanding of long-term environmental patterns. Indigenous observations of weather patterns, seasonal variations, and ecological relationships provide data covering much longer time periods than instrumental records. Integration of traditional knowledge with scientific analysis has improved understanding of climate variability and environmental change. The development of techniques for analyzing oral traditions as historical sources has enabled researchers to extract factual information from mythological narratives. Methods for identifying historically accurate elements within symbolic and narrative frameworks allow researchers to utilize oral traditions as sources for environmental, geological, and astronomical information about the distant past. Interdisciplinary collaboration between archaeologists, geologists, climatologists, and cultural anthropologists has enhanced understanding of the historical value of oral traditions. Combined approaches that integrate traditional knowledge with scientific analysis have revealed correlations and confirmed historical events that would not be evident through any single research method. These collaborations demonstrate the value of oral traditions as sources for understanding prehistoric human experiences. The preservation of detailed technical knowledge through oral transmission demonstrates sophisticated cognitive and cultural capabilities of prehistoric societies. The ability to maintain complex information across many generations without external storage systems required advanced memory techniques, systematic training programs, and cultural institutions dedicated to knowledge preservation. These achievements indicate high levels of intellectual sophistication in pre-literate cultures. Modern recognition of the historical value of oral traditions has led to increased efforts to document and preserve traditional knowledge systems. Indigenous communities worldwide maintain detailed environmental and historical knowledge that provides valuable insights into past conditions and long-term patterns. The documentation and analysis of these knowledge systems contribute to scientific understanding while preserving important cultural heritage. The voices from the earth, preserved in oral traditions passed down through countless generations, offer humanity's longest historical perspective on environmental change, astronomical events, and cultural adaptation. These narrative archives, encoded in memorable stories and maintained through sophisticated cultural transmission systems, provide access to information about the distant past that cannot be obtained through any other source. Their preservation and analysis continue to reveal new insights into prehistoric human experiences and the deep history of environmental change on Earth. 12,800 years ago, Earth's climate changed more rapidly than at any time in recorded human history. Within the span of a single decade, average temperatures in the North Atlantic region plummeted by 15 degrees Celsius, transforming landscapes from temperate forests back to near glacial conditions. This dramatic event, known to scientists as the Younger Dryas, created environmental pressures that may have accelerated human cultural development and technological innovation. The Younger Dryas represents one of the most significant climate transitions preserved in the geological record. Ice core data from Greenland reveals that this cooling event lasted approximately 1,300 years, during which much of northern Europe and eastern North America experienced conditions similar to those of the Ice Age that had recently ended. The abruptness of this change, occurring within years rather than centuries, challenged human communities with unprecedented environmental stress. Archaeological evidence suggests that the Younger Dryas coincided with crucial developments in human technology and social organization. The period saw the emergence of more sophisticated tool-making traditions, the development of new hunting strategies, and possibly the earliest experiments with plant cultivation. These innovations may represent adaptive responses to environmental pressures created by rapid climate change. The termination of the Younger Dryas was equally dramatic, with temperatures rising rapidly to near modern levels within decades. This warming phase corresponded with major changes in human settlement patterns, including the establishment of the first permanent villages and the development of agriculture in several regions. The correlation between climate stabilization and cultural innovation suggests that environmental conditions played a crucial role in shaping human civilization. Paleoclimatic research has revealed that the Younger Dryas was not an isolated event, but part of a pattern of rapid climate oscillations that characterize the transition from glacial to modern conditions. ice cores, and marine sediment records document multiple episodes of abrupt warming and cooling during this period, each lasting centuries to millennia. Human communities during this time faced a highly unstable climate system that required constant adaptation and innovation. The Sahara Desert provides another dramatic example of prehistoric climate transformation with profound implications for human development. 9,000 years ago, much of what is now the world's largest hot desert was a green savanna dotted with lakes and rivers. Archaeological evidence from this period reveals thriving communities that practiced cattle herding, fishing, and possibly early agriculture in regions that are now entirely uninhabitable. Rock art from the Sahara preserves detailed records of this vanished ecosystem. Petroglyphs and cave paintings depict elephants, giraffes, hippopotamuses, and other large mammals alongside scenes of human activities, including fishing, hunting, and cattle herding. The artistic record spans several thousand years and documents the gradual transformation of the landscape as the climate became increasingly arid. The desiccation of the Sahara occurred relatively rapidly, driven by changes in Earth's orbital parameters that reduced summer solar radiation in the northern hemisphere. As monsoon rains decreased, vegetation cover declined, creating feedback effects that accelerated the transition to desert conditions. Archaeological evidence suggests that human communities were forced to migrate toward remaining water sources, concentrating populations in river valleys and oases. This climate-driven migration may have contributed to the development of complex civilizations in the Nile Valley and other river systems. As Saharan populations moved toward permanent water sources, they brought with them knowledge of cattle domestication, plant cultivation, and other technologies developed during the Green Sahara period. The concentration of people and resources in river valleys created conditions favorable for the emergence of hierarchical societies and monumental architecture. The Amazon rainforest provides evidence of another major prehistoric climate transition that influenced human development. During Ice Age periods, much of the Amazon basin was significantly drier than today, with grasslands replacing large areas of forest. Human populations adapted to these drier conditions by developing different subsistence strategies and settlement patterns than those used by later forest-dwelling peoples. Genetic analysis of Amazonian plant and animal species has revealed how Ice Age climate changes affected biodiversity and human adaptation. Many species survived the drier periods in small forest refugia, creating centers of biological diversity that may have also served as refuges for human populations. These refugia may have been crucial for maintaining both biological and cultural diversity during periods of environmental stress. The transition to wetter, warmer conditions in the Amazon began approximately 15,000 years ago and continued for several millennia. As forests expanded and rainfall increased, human communities developed new technologies for forest exploitation, including sophisticated techniques for managing forest resources and creating fertile soils in areas of naturally poor fertility. These innovations enabled the development of complex societies in forested environments. Ice Age climate conditions also shaped human development in other regions through effects on sea level, vegetation patterns, and resource availability. Lower sea levels exposed vast continental shelves that are now underwater, providing extensive new territories for human occupation. Archaeological evidence from these now submerged regions reveals sophisticated coastal adaptations that were lost when sea levels rose with the melting of Ice Age glaciers. The study of ancient pollen preserved in lake sediments provides detailed records of vegetation changes that reflect past climate conditions and human activities. Pollen analysis has revealed how human communities responded to climate change through alterations in land use, plant cultivation, and settlement locations. These records document the interplay between environmental change and human adaptation across thousands of years. Climate reconstruction from ice cores, marine sediments, and other geological archives has revealed that climate instability was a constant feature of prehistoric environments. Human communities developed during periods of frequent climate oscillation, requiring constant adaptation to changing environmental conditions. This instability may have selected for cognitive flexibility, technological innovation, and social cooperation that became defining characteristics of human societies. The correlation between climate change and cultural innovation appears in archaeological records from multiple regions and time periods. Periods of rapid environmental change often coincide with technological advances, social reorganization, and cultural developments. This pattern suggests that environmental challenges stimulated human innovation and adaptation, contributing to the development of increasingly sophisticated technologies and social systems. Modern climate science has benefited from studying how human communities adapted to past climate changes. Archaeological evidence of successful adaptations provides insights into resilient strategies for dealing with environmental variability. Traditional knowledge systems developed during periods of climate instability offer valuable perspectives on sustainable resource management and adaptive planning. The preservation of climate information in natural archives allows scientists to extend understanding of climate variability far beyond the period of instrumental records. Tree rings, coral growth bands, ice layers, and sediment deposits preserve detailed records of past climate conditions spanning thousands to millions of years. This long-term perspective reveals the full range of natural climate variability and provides context for understanding modern climate change. Analysis of prehistoric climate events has revealed that rapid climate transitions can occur within human lifespans. The Younger Dryas and other abrupt climate changes demonstrate that Earth's climate system can shift between stable states very quickly when critical thresholds are exceeded. These events provide important insights into climate dynamics and the potential for rapid changes in the future. The integration of archaeological and paleoclimatic evidence has enhanced understanding of human-environment interactions throughout prehistory. Combined analysis reveals how environmental changes influenced human development, while also documenting how human activities began to affect local and regional environments. This research provides important perspectives on the long-term relationship between human societies and environmental change. International research programs studying past climate changes have revealed global connections in Earth's climate system that affected human communities worldwide. Climate transitions in one region often had cascading effects across continents, creating simultaneous challenges for human populations in widely separated areas. Understanding these connections helps scientists predict how future climate changes might affect different regions and societies. The climate archive preserved in natural systems provides humanity with essential information about environmental variability and change. This record reveals that climate instability was the normal condition during human evolution and cultural development. The ability to adapt to changing environmental conditions has been a constant requirement for human survival and may continue to be crucial for future human success in a changing world. 40,000 years ago, when sea levels stood 400 feet lower than today, early humans accomplished something that seems impossible without sophisticated technology. They crossed 60 miles of open ocean to reach Australia. This remarkable feat required not only seaworthy vessels, but also advanced navigation skills, understanding of ocean currents, and systematic planning for long-distance maritime travel. The colonization of Australia represents one of humanity's earliest and most impressive maritime achievements. Even during periods of lowest sea level, reaching the Australian continent from Southeast Asia required crossing multiple water barriers, including the treacherous strait that separated the Sunda and Sahul continental shelves. Archaeological evidence indicates that humans accomplished this crossing repeatedly, establishing populations on islands and continents that had never before been reached by terrestrial mammals. Recent discoveries in Southeast Asian waters have revealed evidence of sophisticated boat-building technologies dating back tens of thousands of years. Underwater archaeological sites have yielded stone tools and other artifacts that indicate systematic exploitation of marine resources and island-hopping strategies. The consistency of these finds across multiple island chains suggests that maritime travel was a regular activity rather than accidental or occasional occurrence. The development of deep-sea fishing techniques provides additional evidence of advanced maritime capabilities in prehistoric times. Archaeological sites along ancient coastlines have revealed fish bones from species that live only in deep ocean waters, indicating that prehistoric communities possessed boats capable of venturing far from shore and techniques for locating and capturing oceanic fish species. Analysis of ancient fishing equipment has revealed sophisticated understanding of marine ecology and fishing techniques. Bone hooks, composite harpoons, and specialized fishing gear recovered from prehistoric coastal sites demonstrate detailed knowledge of fish behavior, seasonal patterns, and optimal fishing locations. The complexity of this equipment indicates systematic development of maritime technology over many generations. Navigation across open ocean required sophisticated understanding of natural indicators, including wind patterns, ocean currents, and celestial movements. Pacific island cultures preserve traditional navigation techniques that demonstrate how prehistoric mariners could traverse vast distances without instruments. These methods, based on detailed observation of wave patterns, bird behavior, and stellar positions, enabled accurate navigation across thousands of miles of open ocean. The settlement of Pacific islands represents one of the most remarkable achievements in maritime history. Beginning approximately 3,000 years ago, Polynesian navigators systematically explored and colonized islands scattered across an area larger than any continent. This expansion required not only exceptional seamanship, but also careful planning for colonization, including the transport of plants, animals, and essential resources to sustain new settlements. Archaeological evidence from Pacific islands reveals sophisticated planning and execution of long-distance colonization voyages. The species of plants and animals found on different island groups indicates selective transport of useful species rather than random arrival. Polynesian colonists carried pigs, dogs, chickens, and numerous plant species, suggesting systematic preparation for establishing sustainable communities in previously uninhabited environments. The construction of ocean-going vessels without metal tools demonstrates advanced understanding of materials science and engineering principles. Traditional Pacific Island canoes, some capable of carrying dozens of people and supplies for extended voyages, were built using sophisticated joinery techniques, careful selection of wood types, and innovative design features that provided stability and seaworthiness in rough ocean conditions. Recent experimental archaeology has demonstrated the feasibility of long-distance ocean travel using prehistoric technologies. Reconstructions of ancient vessel designs, built with traditional materials and techniques, have successfully completed voyages of thousands of miles across open ocean. These experiments confirm that prehistoric maritime technology was sufficient for the remarkable voyages documented in the archaeological record. Evidence for prehistoric maritime trade networks extends across vast ocean distances. Obsidian artifacts found on islands hundreds of miles from their geological sources demonstrate regular contact between island communities. The distribution of these materials indicates established trade routes and systematic exchange relationships that required reliable maritime transportation. The development of specialized maritime technologies appears in archaeological contexts much earlier than previously recognized. Stone anchors, boat-building tools, and harbor installations found at prehistoric coastal sites indicate that maritime activities were central to many ancient economies. These technologies represent sophisticated adaptation to coastal and oceanic environments. Preservation of organic materials in some archaeological contexts has provided direct evidence of prehistoric boat construction. Waterlogged sites have yielded fragments of wooden vessels, rope, and other nautical equipment that demonstrate construction techniques and materials used by ancient mariners. Analysis of these remains reveals sophisticated joinery methods and careful selection of materials for maritime applications. The cognitive demands of long-distance navigation suggest advanced mental capabilities in prehistoric populations. Successful ocean navigation required mental mapping of vast ocean areas, memory for complex navigational information, and decision-making abilities under challenging conditions. These requirements indicate sophisticated cognitive abilities and cultural systems for transmitting navigational knowledge. Social organization of maritime expeditions required coordination and planning capabilities that suggest complex prehistoric societies. Long-distance voyages demanded cooperation among large groups, allocation of resources for vessel construction and provisioning, and leadership structures capable of managing dangerous expeditions. The success of these endeavors indicates well-developed social institutions and decision-making processes. The impact of sea level changes on prehistoric maritime cultures provides insights into human adaptation to environmental change. Rising seas following Ice Age glaciation submerged many coastal settlements and altered navigation routes, requiring constant adaptation of maritime strategies and technologies. Archaeological evidence suggests that coastal peoples successfully adjusted to these changes through technological innovation and social reorganization. Modern analysis of ocean currents and wind patterns has revealed the sophisticated environmental knowledge required for prehistoric navigation. Successful long-distance voyaging required understanding of seasonal variations in weather patterns, recognition of ocean current systems, and ability to exploit favorable conditions while avoiding dangerous situations. This knowledge indicates systematic observation and cultural transmission of environmental information. The preservation of traditional maritime knowledge in some Pacific Island cultures provides insights into prehistoric navigational capabilities. Master navigators maintained detailed mental maps of ocean areas, recognized subtle environmental cues, and passed complex knowledge to trained successors through oral instruction. These traditions demonstrate the sophisticated nature of prehistoric maritime science. Archaeological investigation of submerged coastal sites continues to reveal new evidence of prehistoric maritime capabilities. As underwater archaeology techniques improve, researchers are discovering harbors, fish traps, and other maritime installations that extend understanding of ancient seafaring. These discoveries consistently demonstrate more advanced maritime technology than previously recognized. The development of maritime technology represents a crucial achievement in human cultural evolution. Mastery of ocean travel enabled human expansion into new environments, facilitated long-distance trade and cultural exchange, and supported the development of specialized coastal economies. These capabilities contributed to increasing cultural complexity and technological innovation. International research on prehistoric maritime cultures has revealed common technological solutions developed independently in different regions. Similar boat designs, navigation techniques, and fishing technologies appear in widely separated areas, suggesting either cultural diffusion or convergent innovation in response to maritime challenges. These patterns indicate fundamental human capabilities for technological development and environmental adaptation. The maritime pioneers, who first ventured across open oceans, established patterns of exploration, colonization, and cultural exchange that continued to shape human history. Their achievements demonstrate sophisticated technological capabilities, environmental knowledge, and social organization that challenge conventional assumptions about prehistoric human abilities. The legacy of these early mariners includes not only their immediate accomplishments, but also the foundation they established for humanity's continuing relationship with the world's oceans. 8,000 years ago, a vast settlement sprawled across the Anatolian plateau in what is now central Turkey. No streets divided this prehistoric metropolis, no central plaza anchored its layout, yet 9,000 people lived in closely packed houses that formed one of the world's earliest urban centers. This remarkable site, known today as Sadel Hoyuk, challenges conventional understanding of how cities develop and reveals sophisticated approaches to urban planning that emerged thousands of years before the rise of famous ancient civilizations. The absence of streets at Sadel Hoyuk initially puzzled archaeologists, but careful excavation revealed an ingenious solution to urban organization. Residents entered their houses through openings in the roof, moving across the settlement by walking on rooftops that formed continuous pathways above ground level. This three-dimensional approach to urban circulation created public space without sacrificing valuable land for street construction. Archaeological investigation has revealed that Sadel Hoyuk sustained its large population for over 1,000 years through sophisticated resource management and social organization. The settlement's inhabitants practiced agriculture, animal husbandry, and specialized craft production while maintaining complex trade networks that brought obsidian, shells, and other materials from distant regions. The coordination required for such activities indicates advanced planning and administrative capabilities. The architectural sophistication of Çatalhöyük becomes evident through detailed analysis of its building techniques and urban infrastructure. Houses shared walls to maximize structural efficiency and conserve materials, while carefully planned ventilation systems managed smoke from cooking fires and maintained air quality in densely packed neighborhoods. Underground storage areas and elaborate interior features demonstrate advanced understanding of construction principles. Recent discoveries in the Amazon basin have revealed evidence of urban settlements that supported massive populations in environments previously thought incapable of sustaining complex societies. Extensive earthwork systems, raised fields, and forest management practices indicate that prehistoric Amazonian cultures developed sophisticated techniques for intensive agriculture and urban planning adapted to tropical forest conditions. The scale of Amazonian earthworks becomes apparent through aerial survey and remote sensing techniques. Geometric earthen structures, some covering areas larger than modern cities, reveal planned landscapes that supported dense populations through carefully managed agricultural systems. These discoveries challenge assumptions about the carrying capacity of tropical environments and the sophistication of prehistoric South American cultures. Carbon dating and archaeological analysis indicate that some Amazonian urban centers reached their peak development over 1,000 years ago. These settlements incorporated advanced hydraulic engineering, including raised fields, canals, and water management systems that transformed seasonal floodplains into productive agricultural landscapes. The engineering sophistication required for these modifications rivals achievements of better-known ancient civilizations. The Indus Valley Civilization provides another example of prehistoric urban planning that achieved remarkable sophistication. Cities like Harappa and Mohenjo-Daro featured grid-patterned street layouts, sophisticated drainage systems, and standardized construction techniques that indicate centralized planning and administrative control. The consistency of urban design across the entire civilization suggests systematic approaches to city development. Analysis of Indus Valley urban infrastructure reveals advanced understanding of public health and sanitation principles. The houses connected to comprehensive sewage systems that carried waste away from residential areas, while public wells provided clean water access throughout urban neighborhoods. This attention to public health infrastructure represents one of humanity's earliest examples of systematic urban planning for population welfare. The standardization evident throughout Indus Valley cities extends beyond infrastructure to include weights, measures, and construction materials. Bricks manufactured in different cities conform to identical proportional ratios, while measurement systems show remarkable consistency across sites separated by hundreds of kilometers. This standardization indicates sophisticated administrative systems and quality control procedures. Göbekli Tepe, though not strictly urban, represents another form of large-scale social organization that required coordination of massive human resources. The construction and maintenance of this monumental complex required systematic planning, specialized labor, and resource allocation that suggests sophisticated administrative capabilities. The site may have served as a regional center that coordinated activities across a wide area. Recent analysis of settlement patterns in prehistoric Europe has revealed the existence of proto-urban centers that preceded the development of recognized cities. These sites, characterized by dense populations, specialized craft production, and evidence of social stratification, represent intermediate stages in urban development that bridge the gap between village and city organization. The concept of invisible cities extends beyond individual sites to encompass entire urban systems that are difficult to recognize using conventional archaeological approaches. Distributed settlement patterns, seasonal occupation cycles, and mobile urban elements create city-like functions without permanent, dense concentrations of population. These alternative urban forms require different analytical approaches to understand their organization and function. Archaeological investigation of tell sites in the Near East has revealed continuous urban occupation spanning thousands of years. These artificial hills, created by successive building episodes, preserve evidence of urban development and transformation over extended periods. Analysis of tell stratigraphy provides insights into long-term urban processes and adaptation to changing conditions. The emergence of urban centers appears to be closely linked to environmental changes and resource management challenges. Many early cities developed in response to population pressure, environmental stress, or opportunities for resource control. The timing of urban development often correlates with climate transitions or technological innovations that enabled new forms of social organization. Social stratification evident in prehistoric urban sites indicates the development of complex hierarchical societies. Differences in house sizes, burial practices, and access to luxury goods demonstrate social inequality and specialized roles within urban communities. These patterns suggest that urban development was associated with increasing social complexity and institutional differentiation. Trade networks connecting prehistoric urban centers span vast distances and indicate sophisticated economic relationships. Materials found in urban sites often originated hundreds or thousands of kilometers away, suggesting systematic trade relationships and possibly specialized merchants or trading expeditions. These networks facilitated not only economic exchange, but also cultural diffusion and technological transfer. The decline and abandonment of prehistoric urban centers provides insights into the vulnerabilities of early urban systems. Climate change, resource depletion, social conflict, and other factors contributed to the collapse of various urban centers. Understanding these failures offers important perspectives on urban sustainability and resilience. Modern urban planning has begun to incorporate lessons from prehistoric urban experiments. Alternative approaches to circulation, resource management, and social organization developed by ancient cities offer potential solutions to contemporary urban challenges. The diversity of prehistoric urban forms demonstrates that cities can be organized in many different ways. Digital reconstruction and analysis techniques enable detailed study of prehistoric urban sites that are partially destroyed or difficult to access. Computer modeling, virtual reality, and advanced imaging techniques allow researchers to visualize and analyze urban spaces in ways that were not previously possible. These tools are revealing new aspects of prehistoric urban organization and planning. The recognition of prehistoric urban achievements challenges narratives about the development of civilization that emphasize only a few well-known centers. The global distribution of sophisticated urban experiments demonstrates that complex society development was a widespread human achievement rather than the product of a few exceptional cultures. This broader perspective enriches understanding of human social evolution. International cooperation in studying prehistoric urban sites has facilitated comparative analysis and broader understanding of urban development processes. Collaborative research programs enable systematic comparison of urban forms across different regions and time periods, revealing common patterns and unique innovations in human settlement organization. The invisible cities of prehistory, whether hidden beneath jungle canopies, buried under accumulated sediments, or distributed across landscapes in unfamiliar patterns, demonstrate the remarkable diversity of human urban experiments. These settlements reveal sophisticated approaches to social organization, resource management, and environmental adaptation that contributed to humanity's long-term success in creating sustainable communities. Their study continues to provide insights into alternative ways of organizing human societies and managing urban environments. Fire transformed everything. Long before humans learned to shape metal, grow crops, or build cities, they mastered the controlled use of fire, an achievement that would prove more fundamental to civilization than any other technological development. Archaeological evidence suggests that human ancestors began systematically using fire over 1 million years ago, beginning a relationship with this elemental force that shaped every aspect of human development. The earliest evidence of controlled fire use appears in sites scattered across Africa, Asia, and Europe, indicating that fire mastery was a widespread human achievement rather than a localized innovation. Archaeological sites preserve hearths, fire-altered tools, and burned animal bones that demonstrate systematic fire use for cooking, protection, and toolmaking. The consistency of these findings across vast geographical areas suggests that fire control was an essential component of early human technology. Cooking with fire fundamentally altered human evolution by making nutrients more accessible and reducing the energy required for digestion. Archaeological evidence shows that controlled cooking enabled humans to extract more calories from available foods while reducing the risks associated with consuming raw meat and plant materials. This dietary revolution may have supported brain development and enabled the evolution of sophisticated cognitive abilities. The development of controlled fire for toolmaking represents another crucial technological breakthrough. Heat treatment of stone tools improves their fracture properties and enables the creation of sharper, more durable cutting edges. Archaeological sites preserve evidence of systematic heat treatment techniques that indicate detailed understanding of thermal effects on different rock types and careful control of temperature and cooling processes. Ceramic production represents one of humanity's most sophisticated applications of fire technology. The creation of pottery requires precise control of temperature, atmosphere, and cooling rates to produce useful vessels. Archaeological evidence indicates that ceramic production developed independently in multiple regions and became increasingly sophisticated over time, with later pottery showing evidence of advanced firing techniques and artistic achievement. The construction of kilns and furnaces demonstrates advanced understanding of thermal engineering principles. archaeological sites preserve evidence of increasingly complex firing installations designed to achieve specific temperature ranges and atmospheric conditions. These structures required sophisticated understanding of heat transfer, combustion processes, and materials science to construct and operate successfully. Metallurgy represents, perhaps, the most technically demanding application of fire technology in prehistoric times. The smelting of copper ore requires sustained temperatures exceeding 1,000 degrees Celsius, achieved through careful furnace design and controlled airflow. Archaeological evidence indicates that prehistoric metalworkers developed sophisticated techniques for maintaining optimal thermal conditions while managing complex chemical processes. The social implications of fire mastery extend far beyond technological applications. Controlled fire enabled human groups to extend their active periods into darkness, fundamentally altering social interaction patterns and community organization. Hearths became focal points for social gatherings, storytelling, and knowledge transmission, contributing to the development of complex cultural traditions. Fire also provided crucial advantages for territorial control and resource management. Controlled burning could be used to shape vegetation patterns, encourage the growth of useful plants, and create favorable hunting conditions. Archaeological and ethnographic evidence suggests that many human communities developed sophisticated landscape management techniques based on systematic fire use. The preservation of fire-making knowledge through cultural transmission demonstrates sophisticated educational systems in prehistoric societies. The skills required for fire production, maintenance, and application could not be learned through casual observation, but required systematic instruction and practice. The consistency of fire technology across human communities indicates effective methods for transmitting technical knowledge across generations. Archaeological investigation of ancient fire installations has revealed remarkable sophistication in thermal engineering. Prehistoric furnaces incorporated features such as draft control, temperature regulation, and specialized chambers for different applications. These installations demonstrate advanced understanding of combustion principles and materials science that rivals achievements of later historical periods. The development of specialized fire tools indicates systematic approaches to thermal technology. Archaeological sites yield evidence of fire-making equipment, temperature control devices, and specialized implements for managing different types of fires. The sophistication of these tools suggests that fire technology was a mature technical discipline with standardized procedures and specialized knowledge. Glass production represents one of the most technically challenging applications of ancient fire technology. Creating useful glass objects requires precise control of temperature, composition, and cooling processes. Archaeological evidence indicates that glassmaking developed in several regions and achieved remarkable sophistication, with ancient artisans producing optical lenses, decorative objects, and functional vessels. The cultural significance of fire in prehistoric societies is evidenced by its prominent role in religious and ceremonial activities. Sacred fires, ritual burning, and fire-related symbolism appear in archaeological contexts worldwide, indicating that fire held deep cultural meaning beyond its practical applications. The spiritual dimension of fire technology suggests that thermal mastery was integrated into broader worldview and belief systems. Regional variations in fire technology reflect adaptation to local environmental conditions and available resources. Different geographical areas develop distinct approaches to fire production, fuel management, and thermal applications based on local materials and environmental constraints. These variations demonstrate flexible application of fire technology principles to diverse conditions. The development of fuel management systems indicates sophisticated understanding of resource conservation and sustainability. Prehistoric communities developed techniques for charcoal production, wood coppicing, and fuel storage that enabled sustained fire use without depleting local resources. These practices required long-term planning and systematic resource management. Experimental archaeology has provided insights into the skills and knowledge required for prehistoric fire technologies. Modern attempts to replicate ancient fire-making techniques, ceramic production, and metallurgical processes have revealed the high levels of expertise required for successful implementation. These experiments demonstrate the sophisticated nature of prehistoric technical knowledge and the challenges involved in mastering fire technology. The global distribution of similar fire technologies suggests either widespread cultural transmission or independent development of common solutions to thermal challenges. Basic techniques for fire production, cooking, and crafting appear in widely separated human communities with remarkable consistency, indicating fundamental human capabilities for technological innovation and cultural development. Modern applications of traditional fire knowledge continue to provide insights into sustainable thermal technologies. Indigenous fire management techniques, traditional ceramic production methods, and ancient metallurgical practices offer alternative approaches to contemporary thermal challenges. These traditional technologies demonstrate sophisticated understanding of thermal processes and environmental integration. The preservation of organic materials in fire-related archaeological contexts provides crucial evidence for understanding prehistoric technological capabilities. Charcoal, ash, and other fire residues preserve information about fuel types, burning temperatures, and thermal processes that would otherwise be invisible in the archaeological record. Analysis of these materials reveals sophisticated fire management practices and technological knowledge. The study of ancient fire technology contributes to understanding of human technological evolution and environmental adaptation. Fire mastery represents a fundamental achievement that enabled human expansion into new environments, development of complex technologies, and creation of sophisticated cultural systems. The keepers of fire establish technological foundations that continue to influence human civilization. The legacy of prehistoric fire masters extends beyond their immediate technological achievements to include their contribution to human understanding of energy, materials, and environmental management. Their innovations in thermal technology established principles and practices that influenced all subsequent technological development. The controlled use of fire remains one of humanity's most fundamental technological capabilities, and the knowledge systems developed by ancient fire keepers continue to inform modern approaches to thermal engineering and energy management. Knowledge flows like water through time, finding channels to survive even when civilizations collapse and libraries burn. How did sophisticated astronomical calculations survive the Bronze Age collapse to resurface in medieval Islamic texts? How did advanced metallurgical techniques practiced by prehistoric Europeans reappear in Renaissance workshops? The continuity question challenges us to understand how human knowledge persists across dark ages and cultural discontinuities. The transmission of astronomical knowledge provides some of the clearest examples of technological continuity across apparent cultural gaps. Greek astronomical texts preserved Babylonian observational data and mathematical techniques that had been developed over many centuries. This preservation suggests continuous chains of scholarship that maintain technical knowledge even during periods of political upheaval and cultural transformation. Medieval Islamic scholars preserved and developed Greek astronomical works that contained mathematical techniques and observational data originally developed by much earlier civilizations. The sophisticated computational methods used by astronomers like al-Battani and al-Biruni incorporated elements that can be traced back through Greek sources to Babylonian and possibly even earlier traditions. This transmission demonstrates the persistence of technical knowledge across cultural and temporal boundaries. The survival of advanced metallurgical techniques presents another puzzle in technological continuity. Methods for producing high-quality steel, creating complex alloys, and achieving precise temperature control appear in widely separated time periods and geographical locations with remarkable consistency. The similarity of these techniques suggests either continuous transmission of knowledge or rediscovery of fundamental principles. Damascus steel production represents one of the most famous examples of lost and recovered metallurgical knowledge. The techniques for creating these superior steel alloys were apparently lost during medieval times, but have been partially reconstructed by modern materials scientists. However, archaeological evidence suggests that similar techniques may have been used much earlier than previously recognized, raising questions about the true history of advanced metallurgy. Traditional craft knowledge often preserves technical information that predates written records by thousands of years. Skilled craftsmen in various cultures maintain techniques for pottery production, textile manufacture, and tool making that can be traced back to prehistoric origins. These traditions demonstrate alternative pathways for knowledge transmission that operate independently of formal education and written documentation. The preservation of traditional knowledge through master-apprentice relationships has enabled technical information to survive across many generations without written records. Specialized craftsmen developed sophisticated methods for transmitting complex technical knowledge through hands-on instruction, oral teaching, and systematic practice. These educational systems proved remarkably effective at maintaining technical standards and preserving innovation across long time periods. Archaeological evidence reveals technological continuities that span thousands of years, despite apparent cultural discontinuities. Similar construction techniques, tool designs, and manufacturing processes appear in sites separated by significant temporal gaps, suggesting that technical knowledge persisted through mechanisms that are not always visible in the archaeological record. The role of trade networks in preserving and transmitting knowledge has been underestimated by many historical analyses. Merchants, craftsmen, and other travelers carried technical information across vast distances and between different cultures. These networks created multiple pathways for knowledge transmission that could survive political upheaval and cultural transformation. Monastic and religious institutions played crucial roles in preserving technical knowledge during periods of social instability. Islamic houses of learning, Christian monasteries, and other religious centers maintained libraries, workshops, and educational programs that preserved scientific and technical information. These institutions provided stability and continuity that enabled knowledge transmission across generations. The persistence of oral traditions in maintaining technical and scientific information demonstrates sophisticated methods for preserving complex knowledge without writing. Indigenous cultures worldwide have maintained detailed knowledge of astronomy, navigation, medicine, and other technical subjects through carefully structured oral traditions that can preserve accurate information across many centuries. Reverse engineering of ancient technologies continues to reveal sophisticated knowledge that was apparently lost and rediscovered multiple times throughout history. Modern analysis of ancient mechanical devices, construction techniques, and manufacturing processes has revealed levels of sophistication that challenge conventional understanding of technological development and knowledge transmission. The rediscovery of concrete technology illustrates how advanced techniques can disappear and later be reinvented. Roman concrete technology, which enabled construction of durable structures like the Pantheon, was apparently lost during medieval times and only recovered during the modern period. However, recent research suggests that similar techniques may have been used much earlier and in other regions. Cultural fusion during periods of conquest and migration often facilitated knowledge transfer between different technological traditions. The blending of techniques from different cultures created opportunities for innovation and knowledge synthesis that advanced technological capabilities. These fusion periods often produced technological achievements that exceeded the capabilities of individual contributing cultures. The preservation of knowledge in unexpected forms and locations has enabled recovery of apparently lost information. Astronomical data embedded in architectural alignments, mathematical relationships preserved in artistic proportions, and technical information encoded in mythological narratives demonstrate alternative methods for preserving knowledge that can survive cultural discontinuities. International trade in luxury goods often required sophisticated technical knowledge that was transmitted along with the products themselves. The production of silk, glass, metalwork, and other specialized products involved complex techniques that traveled with artisans and merchants. This technological diffusion created multiple centers of technical knowledge that provided redundancy and resilience in knowledge preservation. The development of technical literature and instructional texts enabled more systematic preservation and transmission of specialized knowledge. Early technical manuals, workshop instructions, and educational materials provided standardized methods for teaching complex techniques. These written resources supplemented oral instruction and provided reference materials for practitioners. Regional variations in technical traditions reflect local adaptation and innovation while maintaining fundamental continuities with broader knowledge systems. Different geographical areas develop distinctive approaches to common technical challenges while preserving core principles and methods. This diversity provided resilience against knowledge loss while enabling continued innovation and development. Modern efforts to document and preserve traditional technical knowledge recognize the value of informal knowledge transmission systems. Ethnographic studies of traditional craftsmen, indigenous technical knowledge, and informal educational systems provide insights into alternative methods for preserving and transmitting complex technical information. The recognition of knowledge continuities across apparent historical gaps has important implications for understanding human technological development. rather than viewing technology as developing through isolated innovations. It appears that many achievements represent the preservation, transmission, and development of much older knowledge traditions. This perspective emphasizes the cumulative nature of human knowledge and the importance of understanding technological development as a continuous process. Digital technologies now provide new methods for preserving and accessing traditional knowledge that may help ensure continuity for future generations. Documentation projects, digital archives, and virtual reality reconstructions can preserve knowledge in multiple formats and make it accessible across geographical and temporal boundaries. These tools may provide solutions to knowledge continuity challenges that have persisted throughout human history. The continuity question reveals that human knowledge is more resilient and persistent than often recognized. Despite wars, natural disasters, social upheaval, and cultural transformation, essential technical and scientific knowledge finds ways to survive and resurface. Understanding these mechanisms of knowledge preservation and transmission provides insights into human adaptability and the fundamental importance of maintaining diverse pathways for preserving civilizations' accumulated wisdom.